In year 12, you would have learnt the shapes of different molecules due to the number of bonding electrons and the numbers of lone pairs around the central atom. This is based around a theory called the Vsepr theory, so the valence shell electron pair repulsion theory. The valence shell electrons are the ones that are involved in making chemical bonds, particularly covalent, because that's what we're looking at is covalent bonds for molecules, and within polyatomic ions, and due to lone pairs of electrons around that central atom. These both are described as regions of electron density, and because they are negatively charged, then they will repel each other. So they'll get as far away from each other as possible. And you might remember some of these basic shapes that we had. We had when there are two regions of electron density, so something like carbon dioxide, and here's my Lewis structure for carbon dioxide, it would be represented with this diagram. These two regions of electron density here are repelling each other, so to get as far away from each other as they can in three-dimensional space, they will be 180 degrees away, so they will be what we call a linear shape. So anything with two regions of electron density has a linear electron cloud shape. When there were three, so for example methanol, we've got the Lewis structure here showing us 1, 2, 3 regions of electron density. Even though this is a double bond, it only counts as one region of electron density. So it's only, because it's a bond, even though it's got two bonding pairs in there, it only counts as one region of repulsion. So it's got 1, 2, 3, and we draw that like this. 120 degrees, it sits flat, so it's planar, it's the corners of a triangle, an equilateral triangle, so therefore the bond angles, all of them would be 120 degrees. Now, as we go further into our year 13 work, we'll start to understand why these two bond angles are a little bit higher than 120, and this one's a little bit lower. Remember, this one has got lone pairs of electrons on it, so they also are involved, but also double bond, even though it's only one region, does have a bit more of a repulsion than a single bond. And then the last one, sorry, I'm going to have to hold my camera for this one, is when we've got something like methane. So 4 regions of electron density. Here is my Lewis structure showing my 4 chemical bonds, so 4 bonding pairs, 4 regions of electron density, giving us this shape. And it's got some funny stuff in it. It's got some dotted lines and a sort of triangle shape. The dotted lines show that that hydrogen atom is going into the board. And this triangle is showing that this hydrogen is coming out of the board a little bit. In three-dimensional space, it's a four-sided shape, four-sided three-dimensional shape where each side is a triangle. The name of that is a tetrahedral. And I see I've misspelt it, so I'll just quickly fix that. So tetrahedral shape, tetra is the prefix for 4, and when something's a hedron, it's a three-dimensional shape. So a tetrahedron is a three-dimensional, 4-sided shape. An octahedron would be something with 8 sides that are all the same. So that's where the name comes from. So this is just a bit of a recap of last year, that we've got these 3 examples. Now we can of course have examples where the central atom will have no bond, but a lone pair, creating 3 regions, for example, but with a lone pair. That's where we get our interesting shapes being formed. I'll be doing separate videos on the actual shapes so that you can look at those in separation. But what this video is about is this valence shell electron pair repulsion, the idea that these regions of electron density repel each other, and that's what gives us our shape. When we are writing an answer in NCEA, we can actually quote the Vsepr theory as being why these regions repel each other